Hi, physics class. We are beginning week 3 of distance learning. For the first 2 weeks, we've dealt with the subject of fluids, air, and how an airplane wing works, and liquid, water. Those are both considered to be fluids because the molecules and atoms can move. Now we're going to get into a different subject, and this is the subject of waves. The one type of wave we're not going to talk about is probably the one you're most familiar with, which would be an ocean wave. But we're going to talk about the type of waves that carry energy through air or through the universe. And this is how we get all of our energy from the sun. If we didn't get energy from the sun, there would be no life on Earth. There would be no Earth. So we're going to study those types of waves. We're also going to talk about sound waves. So let's go ahead and get started with this. This will be the lesson for Monday, May the 11th, 2020. And it's the introduction to waves. So waves are the main way nature transports energy from one place to another. Waves can move energy from one place to another without being carried by an object with mass. So waves are pure energy. Waves have no mass or weight, but they might use objects with mass to be transported from one place to another. In the first half of this class, we talked about energy being put into an object such as say a soccer ball. And when you kick a soccer ball, what happens is you put energy into the ball carries the energy, and then when it lands, it releases that energy. Or when you hold a ball up above the ground, it has potential energy. And when you drop the ball, that turns into kinetic energy. And once the ball hits the ground, the energy is released. But we're now going to talk about ways that energy can be transported without being put into an object with mass. If the only way that energy could be transported around the universe is being carried by objects with mass, then you just simply have objects crashing into each other all the time, and that wouldn't be much use, and it certainly wouldn't be possible to have life on Earth. So fortunately, there are ways that energy can be carried around the universe without being put in an object with mass, and that's what we're going to talk about in this unit. So, what kinds of waves are there? There are two kinds of waves we will talk about in this class. Transverse waves move up and down as they travel through space. So think of a roller coaster. So there you see an image of a transverse wave as it's traveling through space, and this wave would be traveling to the right. It's moving in kind of this up and down, up and down, up and down fashion, kind of like a roller coaster. It really does move like that. It's not just a graphical image of it. It's actually how it travels through space. The second type of wave is a longitudinal wave, and longitudinal waves move back and forth as they travel through space. So you can think of kind of like a slinky or a spring. They squeeze and then they release, and then they squeeze and then they release. So the word transverse means to cross something. You can see the transverse wave is crossing back and forth across that center line, whereas longitudinal mean they move in the movement of the wave is in the direction of the wave. So they squeeze, release. Okay, what is a medium? A medium is a substance with mass through which a wave moves. Transverse waves such as light can move without a medium. They don't need anything to carry them. That's why they can travel through the vacuum of space from the sun to the earth. Vacuum is just a place. It doesn't have anything to do with it. It's not related to a vacuum cleaner. It just has to do with a place where there's nothing. Nothing exists, not even air. So transverse waves can travel through space. If that wasn't true, then we wouldn't be able to get light and heat energy from the sun. Light waves move faster through a vacuum than they do through a medium such as air. So light waves are a type of transverse wave. They don't require a medium. They can travel through space, and when they do that, they move at the pure speed of light. When light has to go through air, it slows it down just a little bit, not much that we would notice. But when it has to go through a medium such as air, it will slow down. Longitudinal waves, such as sound waves like the sound of my voice, can only move through a medium. Consequently, there's no sound in outer space. Sound waves move faster through a more dense, thick medium, such as water, than through a less dense medium, such as air. So if somebody is banging a hammer 10 miles away underwater, and you happen to be underwater in the ocean, and somebody's banging a hammer 10 miles away on the hull of a ship, of a metal ship, you can actually hear that 10 miles away under the right circumstances. And the sound travels about 4 times faster than it would travel through air. So what are mediums? A medium is a substance that a wave travels through, such as air or water, and it's actually a substance. The better way to say it also is it's a substance that carries the wave. The wave, wave needs the medium. Certain waves need a medium to carry them. Electromagnetic waves do not need a medium, but they can travel through a medium. So again, light waves traveling through air. They don't need the air to carry them, but they can move through the air. Longitudinal waves do need a medium. So a sound wave cannot travel without something to carry it. Either air or water or any kind of a solid could do it as well. So the example down below will illustrate this. The birthday girl is floating in outer space where there is no air with a police car. It's kind of a silly example, but it makes the point. She can see the lights because light waves do not need a medium. She cannot hear its siren because sound waves do need a medium. So she's standing right next to the police car. She can see the lights. She can't hear it. Even if she's only 10 feet away, she can't hear it because there's no air in outer space to carry the sound. What is a transverse wave? Electromagnetic waves are a type of transverse wave. Electromagnetic waves move at the same wave speed in a vacuum. A vacuum is a place with nothing in it, not even air. And this speed is called the speed of light. And it's 300 million meters per second, which equals about 186,000 miles per second. So light is the fastest thing in the universe. There's nothing that can go faster than the speed of light. And just to put that speed into perspective, that's the equivalent of going around the Earth 7.5 times in 1 second. That's how fast light travels. The light that comes from the moon takes about 1 1/4 seconds to get to us from the moon. The light that travels to us from the sun takes a little over 8 minutes to travel to us. What are the parts of a transverse wave? Okay, so now we're going to get into a little bit of terminology. It's not too hard. Transverse waves move in a repeating pattern. Wavelength. A wavelength is the distance between the top of one wave crest. A crest is the term for a top of a wave, and the next wave crest. Amplitude. Amplitude is the distance from the midpoint of the wave and the crest or top or trough bottom of the wave. So the amplitude is the distance. You see that midline running horizontally. The wave goes across that. That's why it's called a transverse wave. So the amplitude is the distance from that center line to the top of the wave, which is called the crest, or from that same center point to the bottom of the wave called the trough. A mistake students sometimes make, it's not the distance from the very bottom of the wave to the very top of the wave. That would be twice the amplitude. So you can see a wavelength there. That line that's down a little bit below wavelength, that white line, it's just showing that the wavelength can be measured from any point on a wave to the same point on the next wave over. But usually we use the crest, the top, because it's easier to visualize. Okay, how is the speed of a transverse wave measured? When a transverse wave moves through space, a wavelength is called a cycle. So the number of cycles that pass a point per second is called the frequency of the wave. 1 cycle per second is called a hertz, abbreviated Hz. So when the wave starts at crest 1, really the wave is moving from left to right in this picture, but if you're at point A, you're looking right down on crest 1. The wave moves to your right as you look at this picture, and 1 second later, crest 2 is underneath you. Again, you're standing at point A, so the wave is moved to the right. That's called 1 cycle. And if it moves 1 cycle in 1 second, then that's called 1 cycle per second, or 1 hertz. And hertz is the unit of measure. It's abbreviated Hz. That is the measure of the frequency of a wave. So this slide illustrates what I was just saying. You're standing at point A. At 0 seconds, so you have a stopwatch, you haven't started it yet, so it reads 0 seconds. Crest 1 is directly below you. At 1 second, crest 2 has moved over to be underneath you. That means the wave is moving to the right. This is a frequency of 1 hertz because 1 cycle has passed you in 1 second. So the way to view these pictures, you'll see these images in the slides this week. It's a before and after picture. So the wave at the top is at 0 seconds, and crest 1 is beneath you, and that wave is moving to the right. So after 1 second, 1 second later, crest 2 has moved down to be right beneath you. So that's what that is illustrating. So that means 1 cycle has passed you in 1 second. Sometimes students ask, isn't that a wavelength from crest 1 to crest 2? And here's the difference. A cycle is simply a movement of the wave. You start at crest 1 at the top, you go down the wave, and you come back up to crest 2, and that's considered 1 cycle. The straight line distance, as you measure from crest 1 to crest 2, if you just drew a straight line between those two crests of the wave, that distance is called a wavelength. So wavelength is a distance. It's measured in meters or millimeters or nanometers or some unit of meters. Just like we've measured distances in the past, we measure in meters. So that's the difference. It does start and end at the same place, a wavelength and a cycle, but the cycle is actually just one full movement through the wave, whereas a wavelength is a distance between the two crests. Okay, so that completes today's lesson. And so what we're going to be doing, I'll just give you some basic questions. Again, the worksheets, as I've mentioned before, is you can either print them out or you can simply write the answers on line paper. In either case, take a picture and upload it to me. If you're having difficulty with the Canvas system, then simply attach it to an email. Now you can go onto your cell phone and download the Canvas app. It's just like downloading any other app. The school that you have to use is San Diego Unified. That's 3 different words. San Diego Unified. UNIFIED. That's the school. Don't put Hoover High or it won't work. That way you can have Canvas. By the way, it should be Canvas Student, not Canvas Teacher. So you're downloading the app Canvas Student and using the school San Diego Unified. If you have any questions, you can email me or call me on the phone. And I'll be in touch with everybody this week. It's important that you make a contact with me. That could be submitting an assignment. I would like everybody to at least check in at the meeting to know that that you're doing fine and that I am staying in touch with you. So for physics, our meeting is Tuesday from 8 to 9:30. You do not have to stay for the entire meeting, but what I will probably do is go through the assignments. And if you want to stay on for the entire time, we can get through all of these assignments in really an hour and a half to 2 hours at the most. And that's for the entire week. You can just get it all done and out of the way. Okay. So it's just an option for you, but definitely I would like you to check in. Okay. That's it for this lesson. We'll see you tomorrow on Tuesday, May the 12th.